Okay, so we're going to do percent composition, and we're going to use that to tie into how we write out empirical formulas. I'm just realizing that my pen is MIA, so I better find that. Give me 1 second. Okay, so percent composition tells you the mass of what percent of the compound is each element. So you take the mass of the element, you divide it by the total mass of the entire compound, and then to turn it into a percent, we multiply by 100. So we're going to do a sample problem. So calculate the mass percent of each element in sucrose. So the first thing you need to do is figure out the molar mass of sucrose. So add up 12 carbons and 22 hydrogens and 11 oxygens. And I do really want you to make sure that you're practicing doing all this stuff in your calculator. I know it seems like ridiculous, like, oh, you know how to use your calculator, but I see a lot of issues with calculators often in this class, so I do want you to be practicing how you do the molar mass and so forth. So I think if you look this guy up, or if you calculate it out, you end up with like a molar mass of 342.3-ish, something like that.
Am I sharing your screen?
Oh, I am not. You are correct. Thank you. Give me 1 moment. All right. Sorry about that. Okay. So the molar mass of this guy, if you calculate it out, is like, I said it was 340. Was it 340 or 342? Anybody get it? 342.3. This is going to be too thick of a pen size for me. Okay. So if you want the percent of carbon, so you'll take percent of carbon is going to be 12 times, because there's 12 of them, 12.01 all over 342.3, the total molar mass of this compound, sucrose. Sucrose is table sugar, like the sugar that you eat. Okay, and then you do it again for hydrogen. So hydrogen is, there's 22 of them. Each hydrogen's molar mass is 1.01 grams per mole, and the total molar mass is 342.3. And then you do it again for oxygen. So percent of oxygen is, there's 11 of them. Oxygen is 16. You divide it by 342.3. And then again, you multiply these guys by 100. And so go ahead and take the second to calculate them out. I'm going to. So give me 3 digits. Okay, so it's 42.1% carbon. It's 6.59% hydrogen. And it's 51.4% oxygen. Okay, so this is percent by mass. All right. And this should add up pretty darn close to 100% because all 3 of these elements make up the total molar mass of the compound. So now the next question asks you to calculate the percentage of just nitrogen, so just one element instead of all elements by mass. And then I give you the formula calcium nitrate. So I don't actually write the formula for you, so you being able to write the formula is important, otherwise you can't correctly calculate this. So let's see, calcium is +2. Nitrate is -1. So I need 2 nitrates in my compound. So it looks like this. Okay. So there are 2 nitrogens in there. Well, you still have to calculate the entire molar mass of calcium nitrate. So go ahead and take a minute. So there's a calcium, there's 2 nitrogens, and there's 6 oxygens. I think it's like 164.09 grams per mole. okay? So they only want nitrogen. So the percent of nitrogen is, there are 2 nitrogens in here. So 2 times nitrogen's molar mass is 14.01 divided by the total molar mass of the compound, 164.09, and then times 100. So let's see. It is 17.1. Give me 3 digits again by mass. Notice there's no numbers in this problem, so I'm just telling you how many sig figs I want. Any questions? Hopefully this is review. Okay. All right, I'm going to skip this for now. We'll talk about this later. All right, so we're going to get heavy into empirical and molecular formulas. Okay, so molecular formulas tell you the true identity of the substance. So for example, ammonium dichromate. Ooh, flashback on polyatomics. So ammonium. Who is dichromate? Anybody want to share?
Cr2O7 2-.
Thank you. So 2 chromium, so like that's the dichro part, and then the 8 part is the oxygens. So if you write this formula, it looks like this, NH4, and then I need 2 of them to balance out the -2 charge in dichromate. Okay, this is its formula. This is its true formula. Okay, empirical formulas are formulas that have been reduced from molecular formulas. Now, some substances can't be reduced, so their molecular and empirical formulas do end up the same. All right, so let's do the easiest kind of example. I give you molecular formulas and I say, okay, find its empirical formula. Well, if you can take any of these elements and that you could divide them by a common number, then it can be reduced. So look at all of these elements could be divided by 12 and reduced. So that means 1 carbon, 2 hydrogens, and an oxygen. That's its empirical formula. This is like the easiest way to do it. Okay, this can be divided by 2, this can be divided by 2, so its empirical formula is NO2. Now be careful, this is acetic acid, but there are technically 4 total hydrogens. So yes, this guy can be reduced. This is divided by 2, this is divided by 2. There's technically 4 hydrogens, so if you divide that by 2, you end up with CH2O. Notice that these guys' empirical formulas are the same, but their true formulas are not. These are 2 totally different substances. However, their empirical formulas are the same because their empirical formulas aren't necessarily the true formula. Now look at silver sulfate. You can't divide this by anything because you only have 1 sulfur here. The 2 and the 4 were good, but the sulfur kind of messes it up. So its empirical formula is the same as its true formula, which is silver sulfate, just like this. They match. They're the same. There's no difference. Question so far? Okay. Then, so this was like the easiest way to do it. Then we get into using percent composition for determining empirical formulas. So they find a compound and they realize that it's 43.7% made up of phosphorus and 56.3% made up of oxygen, and they want to know what the formula is. So the nice thing about this is that we always assume, to make life easier, that we have a 100-gram sample of the compound, because that means we can just rewrite these percentages as grams. We don't need to like do any special work. So instead of 43.7 percent of phosphorus, we write 43.7 grams of phosphorus. And then 56.3% of oxygen, 56.3 is 56.3 grams of oxygen. Now, when we write out chemical, so look at, you have the answer down here, right? When we write out chemical formulas, these numbers aren't in terms of grams. So if we have a mole of this compound, it means you have 2 moles of phosphorus and 5 moles of oxygen. So these grams, we don't write compounds with grams in mind. We write them with moles in mind. So we need to change these to moles. Okay, so we turn grams into moles. That's not too hard. Find phosphorus on your periodic table. It's right here, 30.97. Okay, so 30.97 grams per 1 mole. And oxygen is 16 grams per 1 mole. And you divide these out. I'm going to give you a second to do that. And I'm going to do it as well. This is 1.4-ish moles. This is 3.51875-ish moles. So now I go, okay, I have my moles. So I write phosphorus 1.4, oxygen 3.5. And you go, no, no, no. This is not how we write out compounds. We can't leave them in fractions. They're always whole numbers. So in order to get the best chance at a whole number, you pick the one that's smallest and you divide everybody by that number. So 1.4. So this ends up being 1. And this ends up being 2.5. Ugh, so we still kind of have an issue because we're not going to write the compound like this, phosphorus, oxygen, 2.5. That doesn't make sense. We always write in whole number ratios. So the easiest way to get rid of a half is to multiply by 2, right? So you multiply the phosphorus by 2 and you multiply the oxygen by 2. So the oxygen 2.5 times 2 comes out to be 5. And this is your empirical formula. Look, it cannot be reduced anymore. You can't divide them by any number. Are there any questions about this? This is hopefully review. Okay, let's try another one. So an unknown compound contains carbon, hydrogens, and oxygen. And a pure sample of the compound is found to be 65.6% by carbon and by mass and 9.44 by hydrogen. Notice they don't give you the oxygen. Well, that shouldn't be a problem because if it's this much carbon, this much hydrogen, out of 100%, the rest should be oxygen. Also notice, sorry, I didn't tell you this. This is a free response question from 1998. So this is like before you were born. It was number 2, the second question, and it was the first part. So believe it or not, you guys can actually do parts of FRQs already, and it's not even May. So look at this. So we have 100%, right? The compound is 100%. Get rid of carbon, get rid of hydrogen, and then you'll know oxygen. Okay, so 100 minus 65.6 minus 9.44. So 24.96% of it is oxygen. Okay, now again, we always on these problems assume 100 grams, so that allows us to rewrite the percentages as grams. So now this is 65.60 grams of carbon, right? To write empirical formulas, we need to be in moles, so turn grams into moles. And then it is 9.44 grams of hydrogen. Hydrogen is 1.01 grams per 1 mole. And it is 24.96 grams of oxygen. Oxygen is 16 grams per mole. A good question that I always get asked is how come we're not calling hydrogen diatomic hydrogen? And how come we're not calling oxygen diatomic oxygen? Well, the reason is because hydrogen's diatomic when it's like floating around by itself. The hydrogen and the oxygen aren't by themselves. They're not only with each other, but they're also hooked up with carbon. So these aren't diatomic atoms right now. They're only diatomic when you don't see them hooked up with anything else. So I always get that question, and I think it's a good question, and hopefully that helps answer that for you. So here we go. So this is 5.46 moles, and this is 9.53 moles. Did I do that right? Hold on. Sorry, 9.34. I don't know what the heck I was doing. 9.346, so 9.35-ish moles. And this is 24.96 divided by 16, 1.56. So it's obvious that the oxygen has the least number of moles, right? We can't write a compound with these ugly numbers. So we divide everybody by oxygen's number. 1.56, 1.56, 1.56. So 5.46 divided by 1.56 is, oh, 3.5. Yuck. Okay, well, whatever. We'll try to work out the rest. 9.35 divided by 1.56 is pretty much 6. And then 1.56 divided by 1.56 is 1. Okay? So again, the easiest way to get rid of a half right here is to multiply it by 2, which means you have to multiply everything by 2. So we end up with C7H12O2. So this is the unknown organic compound. There is kind of a method, like how do you know which order to write the elements in? Generally, the order they present them in the problem, so they presented carbon first and then hydrogen and then oxygen, is generally the order you should write them in, okay? Any questions so far? Hopefully most of this is review. Okay, so guess what? You are going to do a multiple choice question without a calculator. So last class kept asking me, when do I use a calculator, when don't I? Any multiple choice question we're going to learn how to do without a calculator. All other problems can be done with a calculator. It's just multiple choice questions that you want to get practicing without a calculator. So you're going to do an empirical formula without a calculator. How crazy is that? All right, here we go. It's a sample of a compound, and I give you 18 grams of carbon, 3 grams of hydrogen, and 8 grams of oxygen. And they want the empirical formula. And you go, oh my gosh, how in the world am I going to do this? Well, I don't know. Let's practice. 18 grams of carbon. Now, if you don't get a calculator, I would not call carbon 12.01. Why would you do that to yourself? You don't get a calculator. Just call it 12, okay? We're trying to do the best we can without a calculator. And then, let's see, 3 grams of hydrogen, 3.0 grams of hydrogen. Now, I realize that hydrogen is 1.01. Don't make your life hard. Just call it 1 gram per 1 mole. Oxygen is nice. It's just 16. So divided by 16. So 8 divided by 16 is a half. So this is 0.5. 3 divided by 1 is 3. So this is 3. Again, these are moles. Now, 18 and 12. What number goes into both of them? Well, 6. So this is 3 over 2. This is 1.5. Okay, so again, easy math. Now, I don't like, so this is obviously the one with the least number of moles. So you divide everybody by that number. Divide this by 0.5, divide this by 0.5, and divide by 3 by 0.5. Now, me personally, I'm not super good with decimals, okay? So to make my life easier, since I don't technically get a calculator, I'm going to rewrite this 1.5 divided by, and then 0.5 is a half, right? So I'm okay with fractions. So like, I know that this is the same thing as 1.5 times 2 over 1, right? This flips up. So that's 3. Oh, sweet. Okay, I can look at this as a fraction instead of a decimal, and maybe it'll work out better. This is just a strategy that I personally use because I'm not super good at dividing by decimals. So look at 3 divided by a half. The 2 flips up, so this ends up being 6, right? And then a half divided by a half is 1. So 3 carbons, 6 hydrogens, and 1 oxygen. So your answer is B. Any questions on that one? So look, we just did an empirical formula without a calculator. That's pretty cool. All right. So this one was B. Okay, phosphoric acid. And then to save you time, they give you the molar mass they want you to use for it. And they want to know what percent of it is specifically oxygen by mass. Now, this is tricky because this requires you to know the formula for phosphoric acid. So phosphoric, it comes from 8. So this is from phosphate. Okay, and to make it an acid, we add hydrogen ions. So we're going to need 3 of this to balance out the -3 charge. So this is phosphoric acid. If you can't write this formula, you pretty much can't do this problem. So they want to know what percent of it is oxygen, just oxygen, by mass. Now, they give you the mass of this guy. They already tell you it's 98. So percent of oxygen would be, there's 4 oxygens. Oxygen is 16 divided by 98. Okay, so what's 4 times 16? You should be able to do that math, maybe not super quick, but you put the 4 down here, 24, bring the 2 over, 4 times 1 is 4, and then 6, so 64 over 98. Okay, you don't get a calculator. This is ugly. Who cares? How close is this number to 100? It is so close to 100, okay? 98 is so close. So I'm just going to pretend it's 100 to make my life easier. So this would be like 64%, right? So you look over here. This is the closest to 64% that there is. So it is very likely, and it is 65%. So you sometimes have to do like some best guesstimating to make your life easier. Are there any questions about this? Okay, so new stuff. So the data table was collected by gravimetric analysis. That just means they're using electronic scales and really, really good, accurate data to figure out this compound, okay? This compound is a hydrate. If you remember, a hydrate is something that has waters attached to it, okay? So they're doing a hydrate. Whoa, sorry, my cursor is going really slow. A hydrate, which is a salt. For the sake of this class, any ionic compound can be called a salt. Yes, it's not table salt like sodium chloride that you're used to. Oh no. Are we all still there? It looks like I was having a connection issue. Uh-oh. Give me 1 second. Okay, so again, this guy, ionic compound, is a salt and it has waters attached to it. That's what hydrate means. Okay. So it's magnesium sulfate. So magnesium is +2 and sulfate is -2. So this is its formula. And then you would write a dot next to here. Sorry, I kind of ran out of room.
The screen not recording you.
Oh, the screen is recording. Maybe I'm not screen sharing. Hold on. Sorry about that. Okay, so magnesium sulfate, so MgSO4, and then you would put a dot and then a certain number, like we don't know, of waters. That's what makes it a hydrate. Remember, we practiced naming that. It was kind of new. So if you look at this problem, they give you the container that they mass it in, okay? And they also give you the initial mass of the sample inside the container. So if you subtract these two numbers, you can get the mass of just the sample of the hydrate. So I'm going to do that. I'm going to have to flip back and forth. So 181.368. Sorry. So 81.368 is the hydrate and the container. Okay. If I go back, what is the mass of the container? The mass of the empty container is 168.386. 168.386. This is the container. So if you subtract them, you will end up with the mass of just the hydrate. So what does that come out to be? 181.368 minus 168.386 is 12.982. Sorry, that 8 is funky, huh? Okay, and this is just your hydrate. Now remember, the hydrate has the salt and the water attached to it. We don't know how many waters. It's going to be our job to find that out. Okay, so now what they've done is if you look at this data table, you can see that they've heated it. They take the sample and they heat it a couple of times. Can anybody tell me how they know that they were okay to stop after the third heating? They didn't do a fourth heating. So they will ask you this sometimes on the test. They'll say, hey, how did you know that you could stop heating? So anybody want to say what kind of indicates the reason that they could stop heating?
I don't know if this is true, but did they calculate the mass for magnesium sulfate?
They are going to, but just based on the data table, how did they know that they could probably stop heating it, that they got rid of all of the water? So between the second and third heating, the mass barely changed, like 0.001. That's not a lot of change. So that's how they could determine that they were done heating. But look at between the first and the second heating. It's almost a 2-gram difference between these two. So obviously after the first heating, they hadn't gotten rid of all of the water. Okay? So now, if in the sample after this, after you heat it, you have what's called the anhydrous, that means without water, salt, meaning in the container, you only have magnesium sulfate because it is assumed that you've gotten rid of all of the water. All right, so I can figure out how much magnesium sulfate or anhydrous magnesium sulfate is in the container because I can take either this experiment or this one. You would not use this one. They were not finished heating at this point. It doesn't matter which one of these you use. You take this, I would use the smallest one, okay? And if you take this and subtract the container for it, you'll end up with just the dry salt. So 174.725. So 174.725. This is the salt, grams of salt. Anhydrous, no water. And you take away the container, which is up here, 168.386 grams of the container. You get the mass of your dry salt. So let's see. If I remember correctly, it's 6 something. 174.725 minus 168.386 6.339 grams magnesium sulfate. Are there questions so far? Okay. Well, if this is the salt and water, and this is just the salt, if I take these two numbers and I subtract them, I will get the mass of the water in there. So 12.982 is salt plus water. Salt plus water. 6.339 is just the salt. So if you subtract them, I will know how much of it was water that got evaporated off. So plus 12.982. All right, so 6.643 grams of it is water. And you go, well, what do I do with this? Well, we're trying to find a formula. So in order to find formulas, what we've been doing is we've been taking every single element, we turn it into grams, or we turn the percent into grams, and then we turn the grams into moles, and we divide by the least number of moles. For hydrate problems, we're not going to break these apart into elements. We're going to leave the magnesium sulfate intact and the water intact. So we're going to go from grams of magnesium sulfate to moles of magnesium sulfate. So 6.339 grams magnesium sulfate. Turn it into moles like you would for an empirical formula. Can someone shout out magnesium sulfate's molar mass when you get it? So a magnesium and sulfur and 4 oxygens. Water is 18.02 grams per 1 mole. Anybody have magnesium sulfate's molar mass?
120.38.
120 sorry, what?
120.38.
38. Okay. So you take 6.339, you divide it by 120.38, and this is like 0.0526 something, something, something. Okay, and then you do the 6.641 divided by 18.02, and this one is 0.36, whoa. 0.368 something, something, something. Okay, so who's the one with the least number of moles? Magnesium sulfate. So you divide everybody by magnesium sulfate. This comes out to be 1. And this comes out to be 7. So there's 1 magnesium sulfate and 7 waters. So what is the formula? Well, let me go up here. The formula is you write 1 magnesium sulfate, MgSO4, and then you draw this little dot, and there are 7 waters. So its name would be magnesium sulfate hepta, because that's what the number for 7 is, or prefix for 7 is, hydrate. So you just did an empirical formula for a hydrate now instead of just a single compound. How are we doing? Any questions so far? Oops. Okay, we are about to do a sample problem of a hydrate for a multiple choice question without a calculator. I know it sounds crazy, but I swear you can do it. Okay, so a 2.7 gram sample of an unknown hydrate. So it's iron 3 chloride, and then we don't know how many waters are attached to it. So they heat it to get rid of the water. They tell you water's molar mass, and they tell you that the mass of the anhydrous, so just the salt after the water's been driven off, they give you its molar mass of the iron 3 chloride, and they tell you how much remains is 1.62. So 1.62 grams of the salt remains, meaning if you take 2.7 and you subtract 1.62, you'll get how much water was in there, because the rest of the sample should have been water. So what does this come out to be? 1.08 grams of water? Okay, well, how do you figure this out? Well, you turn grams into moles and divide by the least number of moles. So let's see. The salt is 1.62 grams. This is the salt. And they give you the salt's molar mass. It's 162 grams per 1 mole. Okay, and then water, 1.08 grams of water. And water's molar mass is 18-ish grams per mole. Okay, now you don't get a calculator. You should see that this number is probably going to be something kind of nice because they look the same. So here's how I do it without a calculator. I go, okay, I'm going to put a fake decimal right here. And I'm going to call this 162 because I know 162 divided by 162 is 1. And then I go, okay, but this really wasn't 162. I got to go backwards 2 spots to get to my original decimal. So this number is 0.01 moles. Okay, and I'm going to do the same thing here. I'm going to put a fake decimal here because 108 divided by 18 is 6. Okay, so 6. Now, 108 is not really the true number. So I'm going to go backwards 2 spots. So it's really 0.06. Okay, so who has the least number of moles? Well, iron, this should be an E. Sorry, that's kind of funky. Iron 3 chloride has the least number of moles, so we divide by that guy. So you end up with one of these guys. and then you divide the 0.06 by that guy. Well, this is easy. Look at, cross off those zeros. 6 divided by 1 is 6. So it should have 6 moles of water. There would be a 6 here. Iron 3 chloride hexahydrate. Do you have any questions so far? So you're taking empirical formulas just a little bit further. We're doing them for hydrates now too, instead of just simple compounds. Okay, everybody take a deep breath. Open, dust off the cobwebs. This is hard. This problem is hard. The concept can be very difficult. This is definitely AP level stuff we're about to do. I'm going to do 2 examples and then we will be finished for the day. I just need you to note that if you find this challenging, you should. This should be challenging. If you don't think it's challenging, I mean, that's great, but this should be challenging. It's probably one of the harder problems you will have done so far in this class, okay? So let's talk about this. An organic chemistry team is designing a new chemical, and they put this solid made of carbon, hydrogen, and oxygen. So it's this organic molecule. How do I know? It has carbons and hydrogens and oxygens in a vial, and they send it off to a company to put it under a tremendous amount of heat and bubble in with oxygen. Okay. Well, okay, so you have this sample. It has carbon. I don't know how many carbons. I don't know how many hydrogens. I don't know how many oxygens, okay? I don't know. You don't know. It's just a sample with carbon, hydrogen, oxygen. And they bubble in excess oxygen, meaning this guy is your limiting reactant. There's going to be leftover of this, meaning this thing completely is gone. Now, you should be able to look at this and identify who the products are. So, who are the products? What type of reaction is this? Organic compound in the presence of oxygen is what type of reaction? Anybody?
Combustion.
Combustion, great. What are our 2 products of combustion always?
Carbon dioxide and water.
Very good. Okay? So this is the hard part. If you look at the problem, they give you the mass of the sample, so they give you the mass of this guy, and then they tell you how much product is made. Now, you guys are used to being given reactants and trying to figure out products. So in this problem, we're technically working backwards. Okay, we're technically working backwards. We're going to take our products to figure out who this guy is. So there's nothing wrong with that. There's no rule that says you can only do stoichiometry from reactants to products. You can absolutely, if you know information about the products, figure out things about the reactants. So here's my point. If they're trying to tell you that this completely combusts, it means that all of the carbon in this compound turned into the carbon in carbon dioxide because there's no other carbon anywhere as a product. And that all of the hydrogen in this organic compound turned into the hydrogen that's in water. Now, oxygen, we can't say the same because there's oxygen here, and there's oxygen here, and there's oxygen here, and there's oxygen here. So if we can figure out how much carbon is in the sample and how much hydrogen in the sample is in the sample, we can figure out the rest must be oxygen because we know how much the sample weighs. Are we okay so far? I see some chats. Oh, good. Okay, here we go. So they tell you that 22 grams of carbon dioxide were produced and 13.5 grams of water were produced. Okay, so my sample is 11.5 grams, and it's made up of carbon and hydrogen and oxygen. And we don't know how many of each. We do not know its formula, okay? I'm sorry, we said we made 22 grams of carbon dioxide. And then they also said they made 13.5 grams of water. Okay? So again, I'm going to write out this reaction. This is not its formula. This is just like a compound. I don't know its formula. Plus O2 makes carbon dioxide and water. Now remember, I said if this completely combusts, all of the carbon and carbon dioxide must have come from this carbon, and all of the hydrogen in water must have come from this hydrogen. So here's what you do. In order to write empirical formulas, we have to be in moles. Is that right? So we're going to turn grams to moles. 44 grams of carbon dioxide in every 1 mole of carbon dioxide. Well, we know that all of the carbon and carbon dioxide had to have come from the organic compound because there's no other sources of carbon. So I'm going to break my carbon dioxide molecule apart into carbon atoms. 1 mole of carbon dioxide has 1 mole of carbon atoms. Why? Because there's 1 carbon in carbon dioxide. And then you say 1 mole of carbon is 12.01 grams of carbon. Now I'm at grams mass of carbon. So let's calculate that out. It's going to be about 6. I think it's like 6 exactly. 22 divided by 44 is a half times 12. So this is like 6.00 grams of this compound is carbon. Okay, and now we're going to figure out hydrogen because all of the hydrogen in water came from the hydrogen in the organic compound. So you turn grams of water into moles of water, H2O. And then you break the water molecule apart into hydrogens. 1 mole of water has 2, right here, moles of hydrogen atoms. And 1 mole of hydrogen is 1.01 grams. So 13.5 divided by 18.02 times 2 times 1.01 is 1.51-ish. 1.51 grams are hydrogen. So if you take your sample that has carbon, hydrogen, oxygen, and you subtract the carbon from it and you subtract the hydrogen from it, you should get what oxygen is. So let's do that. Todd, no. Sorry, my dog is growling. And it is 3.99 grams of oxygen. Okay, it is 6 grams of carbon, and it is 1.51 grams of hydrogen. This is the mass of each element in the sample. So now, this stuff is new. Okay, this stuff is new. What we're about to do is not new. If you know the grams of each element in the sample, you can find the empirical formula by turning grams into moles and dividing by the least number of moles. So the thing we're about to do is not new. How we got here is new and a lot more challenging than just being given like percent abundance and then going into grams and turning grams into moles. It took a lot more work and effort. So that's why this is considered a difficult problem. So now that we're in grams, we can turn grams into moles, divide by the least number of moles, and find the empirical formula. That should not be new for us, so let's do it. Divided by 16 grams per 1 mole. Carbon is 12.01 grams per mole. Hydrogen is 1.01 grams per mole. So this is pretty much 0.250-ish. This is pretty much 0.5. This is pretty much 1.5. Now, we can't write a formula with these ugly decimals, so we divide by the one with the least number. So that's oxygen, so 0.25 divided by 0.25 divided by 0.25. So this ends up being 1 oxygen. What's 0.5 divided by 0.25? to 1.5 divide, oops, 6. Now, so 6. If you look back at the problem, they listed them as carbon, hydrogen, oxygen. So that's the order I want to write the formula in. So let me erase up here. My formula has 2 carbons, 6 hydrogens, and 1 oxygen. This is the empirical formula. What we did here, down here, is not new. How we got to here is what is new and is a lot more challenging, for sure. Do I have any questions about this one? So what I'm going to do is I've just shown you how to do a more challenging problem. I'm going to give you another one. I'm going to give you a hint on the other one, but I'm going to give you a couple minutes because I'd like you to try it on your own. It is just like what we did. Okay, so menthol, which is an oil that comes from mint, is an organic compound. It has carbons and hydrogens and oxygens. If I have 95.6 milligrams of menthol and I'm burning it in oxygen, so an organic compound in oxygen, that's combustion, I get carbon dioxide and water out. What is the empirical formula of menthol? This is just like the last one. All of the carbon in menthol turns into the carbon in CO2. All of the hydrogen in menthol turns into the hydrogen in water. And then the oxygen you can find by default. If I give you a hint, the biggest hint, it will be this to make life easier. Instead of writing this as milligrams, I would rewrite it as grams and work with grams instead. That's my personal opinion. It is not necessary, but in order to find empirical formulas, we need to be in grams and turn grams into moles and divide by the least moles. So it's easier to work with the menthol in grams instead of milligrams. So this is the same as 95.6 milligrams. And I'm going to have you do it from there. So I'm going to unmute myself and I'm going to turn myself off, but I'm going to give you a couple of minutes to see if you can work out this problem based on what we did on the last slides. But I'll be here if you have questions, and I am going to go over it with you. I just want to see if you can try to do it on your own now, given what we've just done.
You're muted. Just FYI.
Yeah, I'm muting myself on purpose because I'm just gonna like work out a little bit of the problem to kind of help people who might be stuck. So I'm not really talking yet. I'm just kind of starting you off to see, to help people who might be stuck.
Oh, okay.
Thank you though. I appreciate it because sometimes I do forget I'm muted. Actually, I do it a lot. If you are finished, I'd love for you to share your formula in the chat. You don't have to, but if anyone thinks they know, I'd love for you to share. I'm still going to keep working this out. Why can't I get rid of this? How do I get rid of this chat? I'm so confused. What's this one doing here? Okay, well that was interesting. Make sure I'm not muted. Okay, I'm not muted. So again, it's the same process. I just was a little bit more of a pain for you because I gave you milligrams to start off with instead of grams. So you had to turn into grams to moles, and then you took the carbon dioxide apart into carbon atoms because we assume that it's complete combustion. So all of the carbon atoms came from the carbon in the compound, and all of the hydrogen atoms came from the hydrogen in the compound, and then we'll find the oxygen by default. So if you calculate this out, let's see, 269 divided by 1,000 divided by 44.01 times 12.01. So we get 0.0734 grams of carbon, and then 110 divided by 1,000 divided by 18.02 times 2, because water molecules have 2 hydrogens in them, times 1.01. This is 0.0123 grams of hydrogen. So remember, this guy is carbons and hydrogens and oxygens. So if this is all of it, if you subtract the carbon from it and you subtract the hydrogen from it, you should get the grams of just oxygen. So let's see. I get 0.00986. Is that right? Does that sound right? So 0.0099 pretty much grams of oxygen. Okay. Whew, so this was the hard part, was getting the grams of each element. The rest of it shouldn't be too bad because now that we're in grams, sorry, that's a 3. Now that we're in grams, we can turn grams to moles, divide by the least number of moles. So I'm going to erase this real quick. Here we go. So let's do carbon first and then hydrogen and then oxygen. 0.0734 grams of carbon. Carbon is 12.01 grams per 1 mole. And then let's do hydrogen. Hydrogen was 0.0123 grams of hydrogen, and hydrogen is 1.01 grams per 1 mole. And then we do oxygen. Oxygen is 0.0099 grams of oxygen, and oxygen is 16 grams per 1 mole. And we calculate all of these guys out. So here we go. Last calculator. 0.0734 divided by 12.01 is 0.006 moles. That's for carbon. 0.0123, I'm sorry, yeah, 0.0123 divided by 1.01 is 0.012-ish moles. And then 0.0099 divided by 16 is, oh my gosh, when I was doing this with second period, or no, was it third period yesterday? I was freaking out. I forgot a 0 and I was trying to do this, and I couldn't figure out like where I went wrong, and I was having like a total moment, and the class has termed it getting they got murphed, meaning I like lost my train of thought and just totally confused them all. So this didn't happen this period. This one has 3 zeros, so this is the smallest one. So divided by 0.006. Divide this by 0.006. Oh, see, I did it again. 3 zeros, 0.0006, 0.0006 divided by, you guys almost got murphed, 0.0006. So the oxygen comes out to be one oxygen. The carbon, when you divide this, you end up with 10 carbons. And when you divide this, you end up with 20 hydrogens. That is a crazy formula. So it is C10H20O. That is the formula, the empirical formula for menthol. Whew. Yesterday, I went to start this problem and I was like, I think your brains are pretty much done at this point. What I did was a lot and what I did was challenging. So I'm going to start off here next week. Please do not forget that you have a quiz, hopefully on Monday. And it's going to be on polyatomic ions, writing out formulas, writing out reactions, predicting products, balancing, all that kind of stuff. None of the stuff we did today, nothing like that is going to be on there. Nothing like that. It's just like writing names, writing formulas, writing reactions, and so forth. If you go to the home page of Canvas, since I'm still screen sharing, I'll show you. If you go to the home page, if you're like don't have your stuff handy or you need to look at it again, if you go to the home page, I've made a button for reference sheets, and so if you click on it, it'll take you to the different reference sheets that we'll use throughout the year so far. I'll probably add to them. But the common ions is right here. So you just click on it and then it'll take you to the link to open up the PDF. And so here it is right here. So you can pull this up if you need to. I am done for today. So if you have any questions, you're welcome to stay on and ask, or you can hang out and start your homework. Some of the homework from last night might have been more difficult without having today's lecture. So you want to maybe go back to that. It might have been challenging because we didn't really talk about hydrates much until today. So I'm going to hang out. You guys are welcome to go. If you want to go, see ya. Have a wonderful weekend. If not, I can hang out here for more questions or whatever you might need.